Welcome back to the channel. This video is going to help you understand the concept of energy in a simplified manner. We will take a look at three laws: conservation, dissipation, and the basics of thermodynamics. Let's start with the law of conservation of energy. This law states that energy cannot be created or destroyed. Instead, energy is transferred from one energy store to another via an energy pathway. Energy can be stored in 8 ways: kinetic, gravitational, chemical, elastic, magnetic, electrostatic, nuclear, and thermal. Kinetic. This is energy stored in a moving object. We can calculate it using the equation Ek equals half mv squared, where Ek is the kinetic energy measured in joules, m is the mass measured in either kilograms kg or grams g, and finally the v is speed measured in meters per second, m/s. We can rearrange the equation to: mass is the kinetic energy divided by half of the velocity squared, and velocity is the square root of the kinetic energy divided by half of the mass. Gravitational potential energy is that stored in an object based on its position in a gravitational field. On Earth, the gravitational field strength is 9.8 newtons per kilogram. The higher an object is through a gravitational field, the more GP it has. We calculate GP using the equation EP equals mgh, where EP is the gravitational potential energy measured in joules, the m is the mass measured in kilograms kg or grams g, the g is the gravitational field strength measured in newtons per kilograms, n/kg, and finally the h is the height measured in meters. Time to rearrange the equation. Mass is the gravitational potential energy divided by the product of the gravitational field strength and height. The gravitational field strength is the gravitational potential energy divided by the mass times the height. Finally, the height is the gravitational potential energy divided by the product of the gravitational field strength and the mass. Chemical energy is stored in chemical bonds and is released when a substance undergoes a chemical reaction. It is most commonly stored in food, fuels, and batteries, and your muscles are a good store of chemical energy as they are mostly powered by food and nutrients. Elastic potential energy is stored in an elastic object that has been stretched or squashed. Note that an elastic object returns to its original shape. This EP depends on two things: the extension, which is how much the object has changed shape in meters, and the spring constant, which is the amount of force needed to extend the object by 1 meter. To calculate elastic potential energy, use the formula EE equals half k E squared, where EE is the elastic potential energy measured in joules. K is the spring constant, which is measured in newtons per meter, or n/m. E is the extension, in which we measure in meters. Let's rearrange the equation then. The extension is the square root of the elastic potential energy divided by the product of 0.5 and the spring constant. Talking of spring constant, this is equal to the elastic potential energy divided by half of the squared extension. Magnetic energy is energy stored in a magnetic field in which the force of magnetism is experienced in relation to a magnet. Electrostatic energy is similar, but with charges that are either attracting or repelling one another. And nuclear energy is stored in the nucleus of an atom. Nuclear energy can be released through processes such as nuclear fission and fusion. Our final energy store is thermal energy, which is actually stored in every object but stored more in hotter objects. The equation we can use is delta E equals mc delta T. Delta E is the change in thermal energy measured in joules. M is the mass measured in kilograms kg or grams g. Now the C represents the specific heat capacity, which is the amount of energy required to raise the temperature of 1 kilogram of that substance by 1 degree Celsius. Check out the video in the description for more information. Finally, delta T is the change in temperature measured in degrees Celsius. So, we've looked at how energy can be stored. But we know that from the law of conservation of energy, it is transferred from one store to another and not destroyed. It can be transferred in 4 ways: mechanical work, radiation heat, and electrical work. Mechanical work is energy transferred when a force causes an energy transfer. In other terms, when something is physically done. To calculate it, we can use the equation W equals Fs, where W is the mechanical work in joules, F is the force in newtons and S is the distance in meters. So, transfers 2 and 3, heat and radiation, link to another law of energy known as the laws of thermodynamics. Heat is transferred from a hotter object to a cooler object until thermal equilibrium is met. Heat can be transferred in 3 ways: conduction, convection, and radiation. Conduction occurs in solids when particles are heated and vibrate. The vibration transfers the heat along the solid by increasing the kinetic store of neighboring particles. Convection occurs in liquids and gases when more dense fluids rise and displace cooler fluids which sink. This forms a cycle known as a convection current. Radiation occurs when infrared is emitted as electromagnetic waves from a surface. Hotter bodies emit more IR than they absorb, and cooler surfaces absorb more IR than they emit. The final energy transfer is electric work, which is energy transferred when a current flows around a circuit. The equation is E equals VQ. In the equation, the E is the electric work measured in joules. The V is the potential difference measured in volts. You may know this as voltage. Finally, the Q is charge, which we measure in coulombs. So, here is an example of the law of conservation of energy. A ball is being dropped. Before it is dropped, it has 100 joules of gravitational potential energy and then no kinetic energy. When we drop it, the GP is converted to kinetic energy via the mechanical pathway. Before it reaches the ground, it has no GP but now 100 joules of kinetic energy. This is theoretical because really it isn't as simple as this. As we will see, not all the GP will transfer to kinetic, but this helps to see that energy isn't created or destroyed, but instead transferred from one store to another. We have looked at the law of conservation of energy and touched on thermodynamics. Now it is time to take a look at the dissipation of energy, which explains why energy transfers aren't as simple as you may seem. In all energy transfers, some energy is wasted to the thermal store of the surrounding, and this is dissipation. So no transfer is 100% efficient due to the wasting of energy. But what is efficiency? Efficiency is the proportion of input energy that is transferred usefully. It doesn't have a unit but a value between 0 and 1, or 0% and 100%. Nothing can have an efficiency of 100% because energy is always dissipated. Nothing can have an efficiency of more than 1 because energy would have to be created. There are 2 equations for efficiency. Firstly, the useful output energy divided by the total energy input, both measured in joules. Secondly, we can divide the useful power output by the total input of power, both measured in watts. So, there you have it. The conservation and dissipation of energy, and a little bit about thermodynamics. I hope you enjoyed it and found it useful. Please like and subscribe. One lucky subscriber in the next month will win £100. So subscribe.